So in the previous example, we saw that this exponential growth can work to your advantage if you're investing money because the amount that you're getting each time gets bigger and bigger and bigger. This can also work to your disadvantage. So if you are accruing interest on a debt, it works the same way. They call that compound growth. Means the amount that it's growing by is increasing at each period. So compound growth has that snowball effect. It gets bigger and bigger and bigger. The bigger the ball of debt, the bigger it accrues more debt, more interest for you to pay off. So a good lesson. Be really, really careful with that as you get older because you guys are only not that many years away from being able to open up credit cards. So here's an example of something that didn't exactly happen to me, but it happens to a lot of young kids when they get their first credit cards because they get these offers that sound great. So in this situation, Michaela leaves for college, starts getting credit card offers, and she gets one. She wanted to buy an iPhone. And a lot of times people open these, they intend to buy a few things, cover a couple of items or whatever, and then pay them off. But then the temptation is too great. They run up the debt all the way to the limit, in this case, $5,000. And they try to tempt you into doing that by having things like no interest for 8 months, which just sounds great. It doesn't accrue any debt. But then after that sort of incentive period, they start racking up the debt. In this case, it's 2% each month. So 8 months go by, she's got that maxed out credit card, and it starts to accrue debt. And so what we're going to do is just imagine what would happen if she didn't make any payments on it. She just let it sit there and accrue debt, more and more debt that would snowball, which is exactly what credit card companies hope that you would do, is just keep putting it off. It's how these banks make a ton of money off of our spending habit. So on this one, we've got a table set up. We're going to see what happens for the first several months and then after the first few years. So a couple ways you could do this. You could take 5,000 and you could multiply it by 0.02. So 5,000 times 0.02, and you would get like $100. Add that on to 5,000, you've got $5,100 after the first period. Now we also know from the previous one though that there's an easier way to do this. We could say, well, if something goes up by 2%, you're multiplying it by 0.02 and then adding it on to the previous number, like we saw last time. You could also just figure out what the multiplier is, the growth factor. So if you do 5,100 divided by 5,000, we get 1.02. And then we do that at each interval to get where she's at after 6 months, and then for each year for the next 4 years. And so I made my table showing that here we've got our 6 month cutoff, and then there's 1 year, 2 years, 3 years, and 4 years. Remember, we're turning those into months. X is months. And so you have to turn those years into months. And if you do that, you'll see it grows pretty darn fast. And when you get to the end of 4 years, you should get that she's at almost $13,000. So she's at $12,935 of debt. So that is more than doubled during that time when she's been ignoring it. $5,000 of stuff has now become almost $13,000 that it's going to cost her. So be warned, this is something that happens to people, and it sucks. So writing our equation in exponential form, we have our starting value, which is $5,000, and then the multiplier, the multiplication factor, 1.02, the power of x, where x is the number of months. And so we want to see how long it'll take to double the first time and the second time. So from 5,000 to 10,000. And then 10,000 to 20,000. So on this one, you'll notice if you look at your data table, You might notice that at 36 months, it was actually just over 10,000. So on your calculator, you don't have to sit there and click on that multiplier starting at 5,000, like 36 times. Because your table actually goes up to near that doubling value from 5,000 to 10,000, you can just do 5,000 times 1.02 to the power of, if we go back to like 33 months, we're almost there. Like I said, you could tell looking at your table, if you did all of those intervals, that it happens right around 3 years. So here is at 33 months. So here is 34, and oh, something went amiss there. So 5,000 times 1.02 power of 33 equals that, and times 1.02. Okay, there we go. So that's 34 months, 35 months, 36 months. So 35 or 36 months, it doubles. And remember, we found with exponential change that doubling period stays the same no matter what your starting point is. So if we want to see how long it takes for that $10,000 to double again to make $20,000, let's use a little bit of reasoning and just make that prediction. So if it takes another 36 months, that means at about 70 months, 72 months, it should be doubling again. So there's 70 months, 71 months right there. It's past 20,000. So the doubling period stays the same no matter what the starting value of that debt is. So it ends up being 35 or 36 months each doubling period.